Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and currently the webinar show is on the road. Once again, we are now in our training room and our corporate office in San Jose, California. So would just like to say thanks again for taking time out of your day to take a look at the topic that we're looking at for today, and that's going to be tips for selecting a torque sensor. Now, typically as we start with most of all of our webinars, we highlight basically a lot of the torque failures that can come with not taking preventative action or not being able to test tools properly. And with this topic, and use of torque sensors, this gives us a good chance to highlight those once again, because if a tool is out on the floor and it's not producing the correct torque, obviously that can be detrimental to the quality that you are trying to produce. And if that fastener fails at some point and it's for an end user or another customer, there can be some real trouble with that. So by using a torque sensor, we can help to mitigate some of the torque failures that may come along with the use of torque tools and help to improve the quality that you are producing. And so what is basically the value of measuring torque? Again, we kind of touched on it there at the beginning just a little bit. Having peace of mind and knowing that your tools are producing the torque that you want them to produce can really help in flushing out root causes for problems within the manufacturing process. If you have a joint that is failing, is it the tool that is producing the failure? Is it the fastener that's producing the failure? Was there a component change? Were there some material changes? A lot of that can be narrowed and focused because we are testing and eliminating one possibility of it possibly being the tool that is causing the issue. We also have the ability to document this type of testing with the use of the torque sensors. This can be great, obviously, to validate and make sure that your tools are producing the torque that is needed in between calibration cycles. So you have that ability to have the documentation, and then there's also traceability that comes with that and the sensor. And we'll talk a little bit more about that when we look at the specific sensor types and such. But there is a really good value to be able to go out and test your tools, have the equipment available to be able to find a problem, fix it, and take care of it right away. If we look at the different stages within the manufacturing process of when we can use torque sensors, along with some torque testing equipment, it's going to be virtually all the way through the entire process, but we can use them prior to the assembly, we can use it during the assembly, and then we can also use it after the assembly. So prior to the assembly, we're looking at using it to set up specific tools to get them to the torque that you would like them to be. Also look at tool capability studies, do some R&D with some of the different sensors. During the assembly, we can actually monitor the tool on the joint and see exactly what's happening to the torque during the assembly process. And that would also allow for torque verification and validation of the tool, that it is performing as intended within the specifications. And then after the assembly, we can also look at auditing specific fasteners or joints, and then we can do tool recalibration as well. So there are a number of different scenarios within the manufacturing process where we can use the torque sensors and that equipment. Now that's going to bring us right to our poll question for today, and we'll go ahead and launch that poll. But we're looking at in your manufacturing process, where do you do the measuring? Is it before the assembly? Is it during the assembly? After the assembly? All of the above, or not at all? So we'll give you just a few seconds to go ahead and respond to that, and take a drink of water. Be back in just a second. All right. Well, we had a really good response, but it is in order of popularity here. It is before the assembly is our winner, I guess, if so to speak, followed by during the assembly, and then after, and then all of the above, and then a few not at all. So very good, and thank you for participating in the poll today. And so as we look at the torque sensors and their specific roles and things that they can do within their scope of use, the torque sensor is basically taking an analog signal, the torque output of the tool, and we're converting it to a digital signal where we can then measure that according to the correlation of the voltage and the output of the tool. And so we'll talk a little bit more about this when we look at some of the animation on how that actually works when we get to that section. But we're basically measuring resistance through an electrified circuit is how the torque sensors are functioning. Now there are each sensor is a calibrated piece of equipment, so it is calibrated to a certain standard. All of the sensors are calibrated using dead weights, and it could be in association with a couple different calibration standards, but each sensor is calibrated to a specific standard. Now, they also have an accuracy statement associated with that. If a sensor is being used with our torque analyzers, we would see a 0.5% plus or minus accuracy of reading during the 20 to 100% scale of the actual sensor. So sensors do have a range that they can test through. And so that would be the accuracy statement for that particular combination of sensor and analyzer. You might see on our site, if you look at a sensor just by itself, there's going to be an accuracy statement of 0.25% of full scale, which means that is going to be accurate without the pairing part of it, but it's going to be a full scale reading, which means that you would take the percentage at the full scale, at the 100% of the scale, and that is going to be the accuracy statement throughout the range of the sensor. And that's different than if you're looking for a sensor that is of reading, because now we're looking at 0.5% of the actual value that we're trying to read. So there is a much tighter tolerance when you're looking at a system that is calibrated together, as opposed to just purchasing the sensor by itself. But nevertheless, just some information on that. All of that is to say that these are sensitive pieces of equipment that are calibrated to a certain standard using dead weights. Now there are two basic standard torque sensors. That's going to be a static sensor and a dynamic sensor. The static sensor is basically measuring torque at one moment in time. A dynamic sensor can be measuring as a tool is in use during a particular tool rundown or application. So this will be a little bit more clear to you as we look at the tools, or actually we look at the sensors during the little demo portion of today's presentation. And so the static sensors are typically referred to as a reaction type of sensor. There is a drive that is on the sensor, and it doesn't move. It is fixed. And so as we apply torque to that sensor, there is a little, for lack of a better word, a bar that is inside there, and that as we apply load to that, there's some torsion that happens, and then we're measuring the torque off of that twisting force that's happening. But with the reaction style transducer, there is no movement in the sensor. So let's go ahead and we can take a look at the different reaction style sensors. And so on our gathering here of our different tools or sensors, actually, we have a couple different analyzers here, our LTT and our Easy Torque 3. Both of these analyzers have a reaction style sensor that is built into them, and they all have a certain range. So this one goes from 5 to 50 foot-pounds. This one goes from 5 to 50 inch-pounds. So these, again, we would be testing directly into the drive of the reaction style transducer. Now the LTT unit does have the ability to expand the range of the sensors. So we can add additional sensors to it that aren't the same range as the internal sensor. So for example, here I have one BMX 100i. So this one goes from 10 to 100 inch-pounds. This one just happens to be the same as the internal transducer here. It's 5 to 50 foot-pounds. And then we have a 5 to 50 inch-pound sensor as well. But these can vary all the way up to 10,000 foot-pounds. It's a little bit bigger of a sensor, but nonetheless. And then we also have very, very small inch-ounce type of sensors, which is going to be our MDX type of sensor. But yeah, this would be on our very low inch-ounce range of testing. And so to give you an idea of what this looks like, if you have not seen that before, we can put our tool into the square drive, and we can go ahead and we would torque it, and it's going to give us the torque output of the tool. And so we can use these types of sensors with hand tools like this preset torque screwdriver. We can also use them with torque wrenches as well. So a same scenario, we would put the tool into the drive, go ahead and cam it, and that is going to give us our torque reading on the analyzer. And then we can also do the same with a power tool. We can use pneumatic power tools. We can use electric clutch tools. We could also use DC type of tools, and the same type of requirement for this is that we cannot take a power tool and we can't go directly into the sensor itself. This is not going to give us a very accurate reading of the torque output of the tool because we're not allowing the tool to ramp up to its running RPM during the fastening process. So to solve this, we use what is called a rundown adapter or a joint simulator. And then this allows the tool to go ahead and come up to its RPM and then clutch or stop when the threaded portion of the rundown or joint simulator is met. And these joint simulators can be orientated for different styles of joints. So it could be a hard joint that you might want to use, or it could be a soft type of joint, and we can set up the rundown adapter to accommodate those different styles of rundowns. And so the reaction style transducer Again, can be embedded into a torque analyzer, or it can be a standalone unit connected to an analyzer, either a mounted unit or also maybe a handheld unit like our PTT as well. We'll take a little closer look at that here when we look at the rotary sensors. But the big takeaway here is that these sensors are, again, the drives don't move. It's reacting to the torque output of the tool, and then it's being analyzed through the analyzer. And there's a couple different modes that can be used, peak mode, track mode, on some number of different things, but that is another webinar discussion on how those function. So that is the use of the reaction style sensor. And so the dynamic torque sensor is going to be the use of a rotary type of sensor. Now this is very different from the reaction one, because now we can put the tool actually on our application. We can run that tool and the sensor is going to be capturing the data as that tool is running down. And so we'll get a final torque and we can get all of that information from the tool on that joint to really help in seeing what an issue might be. Because in reality, if we test a tool on a reaction style transducer, it is reacting to the joint that is present on the sensor. So there could be some joint characteristics that are different between an analyzer sensor or the actual application. So as we run that down, we can see what that difference might be. We can correlate that. And so if we do testing on the reaction style transducer, we know that within a certain degree of uncertainty, what that value correlates to on our joint. So the rotary sensor comes in two different styles of, or two different setups of use. You can use a brush unit or a brushless. If you want to do some testing or more of a constant monitoring type of use for the sensor, then you'd want to use a brushless sensor. If you were doing periodic testing, then the brush sensor would be all right. I don't know if I just meant to brushless for in-use, brush for different styles of uses. If you're going to use it within an application scenario where you want to monitor every rundown that's happening, you'd want to go with brushless. I think I said that right. So nevertheless, that is the rotary sensor. And so this gives us, again, a great deal of information that we can use on our actual joints and our tools. So let's move these guys out of the way just a little bit. Bring our application in here. And so here is an example of a rotary sensor. It's a little bit larger of a sensor, so this one goes up to 100 foot-pounds. It does have a square drive here for the input and for the output. So we put our tool in between here, and then we can measure the torque that's happening on the output. The same scenario would be for this setup here. If we have our analyzer, our PTT, and our rotary sensor, we now can take our tool and we can put that on the input side and go ahead and we can put the tool actually on our application. We can go ahead and we can torque that, and the system is going to tell us what that value is actually on our part, instead of testing it within the reaction style sensor. Now the same setup can also be used with the power tool. So with the power tool, you don't need to use the rundown adapter here. Again, the tool would just come on top through the input. and then we can come to our part, go ahead and attach this or do the assembly process during work and use of the tool, and we're going to see the output of the torque actually on our part. We would also be able to see if there was any prevailing torque as well within that during the rundown portion. So if we wanted to see during the thread engagement portion without taking the fastener all the way to a mating surface, we could then go ahead and measure a prevailing type of torque or any type of run-in torque as well. So that is the use of the rotary sensor. Again, this can be used on the production floor. It can also then be used again to audit a fastener after the fact that we have gone through and done some testing. So there are a little bit differences obviously between the two, but we also can use those for specific purposes within the system. And so a sensor, a rotary sensor, can also be attached to the LTT analyzer, and also a rotary, or excuse me, a reaction style BMX sensor can be attached to the PTT. So all of these sensors can be incorporated with the different systems, the PTT or the LTT, to help expand the range of the testing that you might be doing. So, all right. So that's going to give us to kind of a point of understanding how these sensors actually work. And so we'll first take a look at the BMX sensor. It uses a strain gauge, an electrified circuit, again on a piece of stock that is inside of the housing. As we apply load, there is torsion that is in that fastener, or excuse me, in that stock, and we can then measure what the resistance is to that circuit at different points, giving us the ability to take an analog signal and then convert it into a digital signal. Now the same, here's a quick look of what a strain gauge might be looked at. And this is, depending on the size, excuse me, that could be about half the size of a postage stamp or less. Depends on the range that we might be dealing with. For the rotary sensor, the strain gauge is being monitored through slip rings, and we're then measuring at different points through those rings what the actual resistance is as the shaft is rotating. So a little bit different than the reaction style transducer, but again, we are measuring the resistance that's happening through the circuit. And often what happens is if a sensor gets applied with too much torque that's outside the range of that, then that's where we have an over torque situation where there might be an offset that you would see because the gauge itself has been applied with so much torsion that it ends up breaking that little sensor. And so when we look at the different scenarios of what type of sensor you would want to use in what type of scenario, this gives you a good representation of what you would use a specific sensor for. So for calibration, we'd want to use either the MTX or a BMX sensor, or a sensor that's in one of the torque analyzers. For joint analysis, we can use the rotary sensor, again, because we're measuring the tool actually on the joint that we're doing the assembly on. If we want to monitor a tool or an application all the time, so a constant monitoring type of situation, we'd want to use our brushless rotary sensor. For torque verification and torque validation, we can use basically all of those sensors. If we want to do some process control capability type of studies, we would use the rotary sensors, and then for fastening auditing, where we're going to be looking at torque that has been applied already to a fastener, we would want to use the rotary type of sensor. And so I hope this gives you a good understanding of the two different types of sensors, where they can be used, and how they can be used to help improve the quality within your process. And so with that, that's going to lead us to our questions and answers. We'll take questions from you, and I'll do my best to answer those now. So Chris, do we have any questions?
Morning, Dave. Yeah, we have a few questions to start off with. Regarding the joint simulator, is it necessary for it also with the air power tool?
That's correct. Yeah, any type of tool that is going to produce an RPM, we'd want to go ahead and use the joint simulator on. If it's a hand tool, a torque screwdriver, a torque wrench, we don't have to use the rundown adapter, but any type of power tool you would want to use for that. The only power tool that you don't want to use on any of this equipment is going to be an impact wrench. So pneumatic tools, electric tools, pulse tools, hand tools, all of those are acceptable to be used. The only thing we don't want to use is going to be an impact wrench because there's really no torque control to that, and it can really end up damaging the sensor.
All right. The next one was, what is the difference between a tool's accuracy and repeatability?
So the accuracy is going to be how well that tool meets a certain target, and then the repeatability is going to be how well a certain point within that those targets is that tool being met. So if you have a tool that is performing very repeatable, let's say, for example, we're looking at a scenario where we have a tool that needs to be set to 10 inch-pounds, and that tool is actually, we're seeing it at 9 inch-pounds, but it is repeating at 9 inch-pounds with very well. That would be a very repeatable tool, but just not accurate. So we would need to adjust the tool so it is now meeting the 10 inch-pound goal, and the repeatability of that still is very good around that 10 inch-pound goal. So.
All right. One question that was asked was, what drivers have continuous torque monitoring, Dave? I think you made a comment.
So the rotary sensor will allow you to be able to monitor the tool from the moment the trigger is pulled until it actually torques out. So, and we can capture that data during that rundown portion. If you want to use a sensor within the assembly process where you want to monitor that tool all the time to make sure that the torque could be a very critical type of application, and we want to make sure that that torque is always being met, we would want to use the brushless rotary sensor because there's no contact between it and the shaft as it would be with a brushed rotary sensor.
All right. Next question is, what causes rundown device degradation, variation between rundown devices?
So it's going to be basically the what the joint characteristics of each of those devices might be. And so you can see some variation in the torque output based off the rundown adapter and how that is configured. In the rundown adapter, as I was showing, it does have a series of washers that are beveled, and they can be either stacked nested, or we can go ahead and stack those opposing each other to either make a hard joint or a soft joint, or you may be looking at a spring rundown adapter, or maybe a series of washers rundown adapter. And so those different characteristics within the actual setup of that rundown adapter can show what the differences might be within that. If it is a fastener type of rundown, then obviously we would be using, there may be some loss of clamp force within that fastener itself. So if that is the case, then so many rundowns, that fastener should be removed from the adapter, or replaced, actually, sorry.
All right. Another question we have is, can a rundown adapter simulate both a hard joint and a soft joint? Is there a specific rundown adapter by joint type?
Yeah, it can be. It would just have to be set up for each scenario differently. So you could have one, depending on the kind of adapter. That may not be very efficient, but it could be done. It would probably be better to have one that's set up for a hard joint, another one that's set up for a softer joint, and to be able to do that style of testing, other than trying to.
Okay. Another question is there a process that you can implement to really check the calibration in between designated calibration cycles, like less than 6 months, like a torque measurement program? Or a verification program?
Yeah, so that would be more of a torque verification or validation, where you have a periodic time in between the calibration cycles where you test your tool to make sure that it's still within the calibrated limits of the tool itself. Because the last thing you want is to send a tool out for calibration and it comes back as found out of calibration. So you really have no idea at what point did that tool go out of calibration while it was being used. But if you have a way to test that tool on a periodic basis, say it's once a week, once a month, once every 2 weeks, once a shift, that type of thing, you can then begin to track the performance of that tool and make sure that if it is showing signs that it is drifting out of calibration, that it either is adjusted or that tool may be sent to look to see if there's something else that's going on and if it needs any type of repair. So the torque verification process really can help improve the overall quality, because the tools are producing the torque that's needed within their calibrated range.
Okay. Is it possible to have like calibration equipment in-house to calibrate like dead weight stuff as well, or does it always have to be sent out to a cal lab?
So if you have the capabilities of using segment arms and dead weights and brackets to be able to mount the sensors, that is something that certainly can be done in-house to calibrate the sensors themselves. If you don't, then they can simply be sent to us for calibration, or to another third-party calibration house to be able to calibrate those. But if you have the capabilities and the investment to purchase segment arms and weights, then that certainly can be done.
All right, Dave. We have numerous other questions. I think we can be able to follow up on the post email stuff. Some get into specifics of stuff, so okay. I think we can wrap it up.
All right. I just want to say thank you very much for joining us again on this webinar, and we look forward to seeing you again next month. So have a great day, and thank you very much.